All right, so we just introduced section 1.1. We went over basically the radian calculations. So let's get into our, what page were we on? 6. Yeah, so we had just started with this one. Did you guys have any question about what we did last time before we move on? All righty. Okay, so the last thing I had just kind of talked about was this conversion between degrees and radians. So again, you kind of have to remember these conversion values. So if you're going from degrees to radians, basically that 180 degree conversion is going to be on the denominator. So you have pi over 180 degrees, and then of course if you're going from radians to degrees, you're just inverting that value, so you have 180 degrees over pi. So what I would basically ask you to remember is this relationship here, right? So pi is 180 degrees, and we had kind of seen that last time. So the only thing you really want to remember is if you are getting rid of the degree measurement, it's going to go on the denominator. If you're getting rid of the radian measurement, then the radian is the one that goes on the denominator. And some of your basic angles in both radians and degrees, and this will really help your life a lot if you remember the equivalency between your radians and degrees. So pi over 6 will be 30 degrees, pi over 4 is 45 degrees, pi over 3 is 60 degrees. Of course, pi halves is 90, pi is 180, 2 pi, double that makes it 360. So we're saying when no units of angle measure are specified, that basically means if you don't see any degrees written in there, it's not a degree measurement. By default, it's radians. If they say theta equals 30, don't assume it's because it's in number form that it's a degree. You have to specifically have that degree unit on that. So basically we are implying that when no unit is mentioned, it has to be radian. And as we get into more examples, you will see that your radians are not always just with the pi notation. You can see like this example here, theta equals 2, which means again, that means it's 2 radians and not degrees. So just your basic conversion example here, if you're going from degree to radians, remember what I said, put that 180 degrees on the denominator of your conversion. So it's going to be pi over 180, and then simplify that, you will end up getting your answer in radians. I know we use calculators for our conversions calculations here, but we don't really write radians as decimal values, okay? So you will put your answers in simplified fraction, and then the pi will stay as pi. We don't, unless we're doing calculations, we will not need to convert that pi into a decimal approximation. So same thing here with 540 degrees. You're basically dividing the 180 into 540, which ends up giving you the 3 pi. So let's go ahead and take a look at our example here. Again, I'm specifically saying don't use a calculator. You can if you want to simplify your fractions, but not as decimal answers. So what do you think those 60 degrees will end up being in radians? Yeah, we actually looked at that. But this guy is like 3a. So all you are doing is taking that 60 degrees and multiplying it with pi over 180 degrees, right? And like I said, once you start remembering these conversions, some of these you may not even need the formula for. If it helps, you can write it as 60 over 1, doesn't really matter. But we know 6 goes into 18 basically 3 times, right? So 60 will go into 180 3 times, and this is where you end up getting pi over 3 radians, or you can actually just write it as RAD for short. What was our other angle? 320 degrees. Alrighty. So for 320 degrees, same thing, you're getting rid of degrees, which means pi goes on the top, 180 will go on the bottom. So how many times will 320 reduce into 180? Is it an even cancellation? No, right? Because 180 would actually go into 360, not 320. So how do we reduce that fraction? You're basically looking at, if you ignore the zeros, 32 divided by 18, what will that reduce into?
16 over 9.
Yeah, because 2 is so the only number that's going to be common between them. You can also, like I said, use your calculator just to reduce your fraction. Don't give me a decimal approximation. So 16 over 9 pi radians is what your answer should be for this guy. Okay, so this was going from degree to radians. Now I'm going from radians to degree. Remember, you're just inverting that conversion factor. So now 180 degrees goes on the top, pi will go on the bottom. So let's see. This is number 4. Part A, what are we looking at? Pi over 6. And of course, this is in radians. So 180 degrees on the top, pi on the bottom. What did we end up getting for this guy?
30 degrees.
30 degrees, yeah. And again, we did see this same calculation before. So basically, your pi and the radian unit ends up canceling out. You're just doing 180 over 6. Now, make sure you are using that degree notation, because as I just mentioned, if there is no unit on your angle, we assume it's radian. So you do have to remember to use your notation for the degrees. And our part B was 5 pi over 3. What does that come out to be?
300 degrees.
So again, 180 degrees on the top, pi on the bottom. And you can see the way this formula works out. If you do have that pi value in your radian measurement, they will end up canceling each other out, which makes it really nice and easy. So 3 will go into 18 6 times, so that's 60. Yeah. 300 degrees. Okay. Questions on any of these conversion values? So like I said, as long as you remember pi radians equals 180 degrees, you should be pretty comfortable making that conversion. Again, I would definitely ask you guys to practice with that a little. Let me know if you have
So what did you get the last one?
the last one. Not 300 degrees.
Oh, okay.
Did you not get that?
I was trying to figure out how you did.
Okay, so what I did was divided the 3 into 180, but you can also do multiplication, of course. But I just need it to be easy, right? So you divide these 180, that's 60 times 5. There you go. Did anybody have a question on that? I guess I did kind of go a bit quickly through this last one. Are we okay? Yeah? All right, wonderful. So let's get back to our handout. So here we're looking at, they're saying with calculators it is convenient to use decimal degrees to denote fractional parts of degrees. But normally, you know, when you get fractional answers for degrees, we do like to convert them into minutes and seconds. So just as a notation, we use just a prime notation for minutes and then the double prime notation for our seconds. So basically, if you're looking at value like this one here, you're basically saying your angle is 64 degrees, 32 minutes, and 47 seconds, and this is your conversion factor. Now we know a minute, or basically an hour is 60 minutes, so a minute would be 1/60th of an hour, so that's with the 1 degree multiplication. And a second would be, if you think about it, if there's 60 minutes and each minute is 60 seconds, right? 60 times 60 gives you the 3600. So a second is 1/3600th of an hour, and then you're multiplying that with 1 degree. So I think as we were finding our degree radian keys last time on your calculators, we did find this. So I know you guys on your calculator, that's right, you have the little degree prime and double prime notation. On these calculators, yeah, it's next to the probability key. So you should see the degree prime and double prime key on this. That's the same calculator you have. I'm not sure on
I have the other
your.
one too. I'm not sure where it is on this one.
Okay. Oh, you may actually have to go under.
Basically.
No. And then radian degree.
Okay, and then do you have the conversion for your degree minutes and seconds?
I think so.
That might be something you might just have to play around with.
Yeah.
And see how that works. Alrighty, so basically as long as you can remember these two conversions, you guys will be okay of going back and forth. Otherwise, like I said, you do have your calculators to use with that, and we'll definitely look at that later as we come across it. I actually do want to get into this application here. So we had talked about this a little bit when we first introduced radians. So we had talked about, remember, if your arc length is the same as your radian, that's when your degree is going to be 1 radian measurement, right? So we're actually coming back to that idea here. We're saying to measure the arc length along the circle, your formula was theta equals arc length s divided by the radius r. So you're still using that same idea here, but we're just rewriting that formula. So the idea is, if you wanted to find what the arc length of your circle is going to be, or that specific section, it's going to be s equals r times theta, right? So radius times your measurement. But for arc length, and this is something you will really have to be careful about, your theta for the arc length calculation is always going to be in radian. So what happens is, and you will see this in your homework also, on purpose, they're going to give you your angle in degrees, because they want you to remember that when you're calculating the arc length, you need to convert your degree into radians and then use this formula s equals r times theta. Okay, so be very, very aware of the fact that a lot of times they are going to give you your angle measurement in degrees on purpose to throw you off. So it's these little things that we'll see a lot of errors happening. And again, keep in mind, if your radius is 1, that's when your s value is going to be equal to your degree measurement. So just an example here, we're saying a circle has a radius of 4 inches, find the length of the arc intercepted by the central angle of 240. So basically we're saying if this arc length is what we're trying to calculate, formed by the degree 240 degrees, radius is 4. And remember what I said, they give you your angle in degrees. So that's actually going to be our first step. Take your degree measurement, convert it into radians by using pi over 180. And our radian measurement for that same angle comes out to be 4 pi over 3. And now we're ready to put it into our arc length formula. Radius is 4 inches, so 4 times 4 pi over 3. And it's okay to put decimal approximations for your arc length. What I recommend using is the pi key instead of typing in 3.14. Because if you just do 3.14, your decimal approximation will be incorrect. So just press the pi key and you will get the answer. And so, of course, keep in mind that since you are still talking about the length, if your radius is in inches, your arc length will also come out to be in inches. So let me see what we can do here for number 5. Again, you should notice that that degree measurement, angle measurement is given to us in degrees. So they're telling us a circle has a radius of 27 inches. We're finding the arc length for an angle of 160 degrees. Okay, so let's convert that angle first. And what do you think this guy comes out to be in radians?
Very nice.
8/9 and what else? Yeah. Yeah, very good. So it's going to be 8/9 pi in radians, right? All right, that's it. And now we can use our arc length formula. So that will be radius of 27 inches multiplied with 8/9 pi radians. And like I said, for this guy, you can do a decimal approximation if you like. And since in our example, the answer was rounded to 2 decimal places, we'll use that same rounding here. So can you tell me what that answer comes out to be? 2 decimal places.
It's 3.9.
And then you have an 8 after that. Okay, so just make it 40 to
40.
give you that 2 decimal places. So the raw answer is this. So with 2 decimal places, okay, very good, 75.40. Now you will actually see different types of examples for the arc length. Some of them can actually be more in terms of an application than just generic of this is the radius, this is the angle kind of thing, but you're still using the same concept here. Alrighty, did you have any question on that arc length example? Okay, right, let's get into a little bit more of these applications. So they're saying the formula for the length of a circular arc can also be used to analyze the motion of a particle moving at a constant speed along a circular path, and that's kind of what we're getting into. So before we look at the example, let's look at a couple more formulas here. So we're talking about your linear speed and angular speed. So as it's saying here, consider a particle moving at a constant speed in that circular arc, right? With the radius r. So if s is the length of the arc traveled in time, your linear speed, we're using little d for that, is going to be the arc length. So that's our r times theta, or s, divided by t. And again, we're saying your theta is going to be radian measurement. That corresponds to the arc length. Then your angular speed, that's actually omega. It looks like a W, but that's your Greek letter omega. So that's going to be our central angle, which is of course your theta, again, divided by time. So linear speed is the arc length, s over t. Angular speed is your angle, theta, divided by t. So if you just do a little substitution here, you can again see, since we define s as r times theta, you can do r times theta over t, but remember, theta over t is your angular speed, so you can actually do radius multiplied by the angular speed to get your linear speed also. So it's really going to depend on the application and what information they throw at. So a lot of times, you may have to do the 2 separate calculations, but sometimes they may give you the angular speed and ask you to find the linear speed, or vice versa. All right, so let's look at our example here to try and use this. So the second hand of a clock is 10.2 centimeters long, and you can kind of see that in the illustration here. They're asking us to find the linear speed of the tip of the second hand as it passes around the clock face, right? So obviously it's still talking about that arc length in terms of the linear speed here. So we'll have to do a little bit of calculation here. Of course, one revolution around the circular face means you're going 360 degrees, right? So in radians, 360 degrees is 2 pi. So that's your theta. Then radius is, of course, the length of the second hand, which they're telling us is 10.2 centimeters. So that's basically where your 2 pi is coming from, the entire rotation around the face of the clock. 10.2 is how long the second hand is. So that gives us our arc length, which is 20.4 pi centimeters. Now you'll notice they kept the pi as it is, right? They didn't take that into the calculation. The time required for the second hand to travel this distance, of course, the second hand makes a whole revolution in a minute's time, right? So obviously that means your time is going to be 1 minute or 60 seconds. So finding your linear speed is now taking that arc length divided by your time. So 20 pi over 4, which is what we calculated here, divided by 60 seconds, you've got your linear speed, right? So basically in each second, that second hand is covering 1.07 centimeters for this particular clock. So we're kind of using that same idea here with our example. We're saying the clock, second hand of a clock is 8 centimeters long. And again, they want us to find the linear speed of the tip of that second hand. So similar example, we're just using a different measurement for our second hand. All right, so pretty much similar kind of calculation. Where do you start with this guy?
That's equals 2 pi.
There you go.
8.
Yeah. So this is, oh, where did I put him? All right, number 6. Okay, so the radius for us is 8 centimeters. We are talking about making a full revolution around the face of the clock. So that's going to be r times theta, which is 2 pi r. R is 8 centimeters. So what does that end up giving us for the value of S?
50.27.
So leave the pi as it is.
Oh.
16 pi. Yeah, so you're literally just multiplying 8 times 2 and getting 16 pi. And remember, this will be in centimeters since that's what our radius is. And now to find the linear speed. So time will be, again, it's a second hand, which means in a minute it does the whole revolution. So that's 60 seconds. Okay. So for our linear speed, that's arc length divided by time. Arc length was 16 pi divided by 16 seconds. So that's centimeter over seconds. And what does that guy simplify to? Now this one you can multiply.
Is it 0.83 or 0.84?
Okay, yeah, let's do 2 decimal places. So what's your raw answer?
4, is that divided?
Yes, 8377. So 0.8377. If you're rounding this to 2 decimal places, that's going to be our linear speed. 0.84 centimeters. And it makes sense, right? Because the length of our second hand is less than the example we had seen, which was what, 10.2 centimeters? So if the second hand is of a shorter length, then that definitely means your clock is also going to be of a less diameter than the other one. which means it's going to cover a little bit of a less distance. So again, remember here, by default, your theta has to be in radians. We found the arc length first and then use that to find our linear speed. Any questions on number 6? We're okay? All right, another example, again, using our angular and linear speeds. This time we're looking at a wind turbine. So they're again telling us that the blades of the turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. So they are asking us to find the angular speed of the propeller in radians per minute and also asking us to find the linear speed of the tip of the blades. So let's take a look at this guy. So since we're talking in terms of revolutions for the propeller, obviously, again, a revolution is going to be an entire circle, so that means it is going to cover a distance of 2 pi or the 360 degrees, right? So they're telling us the propeller is rotating or making 15 revolutions, right? So if each revolution is 2 pi, that's going to be 15 multiplied by 2 pi, which gives you your 30 pi radians per minute. And taking that calculation, we can actually calculate our angular speed. So that's 30 pi divided by the revolution is given to us revolutions per minute, which means it's happening per minute. So that's going to be your time. You don't have to figure out the time calculation here. So that actually just comes out to be the same value, your 30 pi revolutions or radians per minute in this case. Now this is where we're actually going to be using the idea of r times theta to calculate our linear speed. So we know theta is 30 pi because that's how many revolutions it's making. So that's your calculation we did from here. Radius, they're telling us the length of the propeller blades, which was 116 feet. So that's going to be 116 multiplied by the 30 pi. Time is still 1 minute. You're actually looking at 10,933 feet per minute based on that. So given the length of the propeller and just the revolutions per minute. So using that idea of 15 revolutions per minute, we know each revolution is going to be 2 pi. Multiply the number of revolutions with your degree, 2 pi, which gives you a total of 30 pi. So in 1 minute, it's covering 30 pi radians, right? That's how many times the theta is working out to be. So that's our theta divided by time, which is 1 minute. So using that same value for theta, you're just multiplying it with the radius to get your linear speed. Okay? All right, so our example again is very similar to that. We have a circular blade on a saw, which has a radius of 4 inches. And this one, because obviously it's a smaller machine, you're looking at 2,400 revolutions per minute. So again, they're asking us to find the angular speed and the linear speed for this guy. So let's write down this information. Number 7. They're telling us the radius is 4 inches and we have or technically, we can actually call them RPMs, right?
Yeah.
Okay, so again, following that previous example, what do you think our theta calculation will come out to be? Yeah, same thing, because you're still making that one full revolution, right? Which is, again, you're using that full circle, so that's going to be 2 pi, and then multiply with your number of revolutions, so that's still 2,400 for this example. So what's 2,400 times 2?
4,800.
Yeah, there you go. So 4,800 pi, and then of course this is in terms of radians per minute. Okay. Alrighty, so angular speed, what will that calculation come out to be?
So 4 times 4,800
No, that's the linear speed.
Oh. And just
So angular speed is the omega, right? Which is theta divided by t, right? So that's going to be our 4800 pi. And we are talking about time as 1 minute. So what does this guy come out to be?
4800.
Yeah, just like you saw in the example, this will also come out to be 4800 pi radians per minute. And that's because we're still doing this over 1 minute as time, right? So your answer really stays the same as what the theta comes out to be. It really doesn't change. So this guy was part A. Part B is the linear speed.
Which is just 4 times the.
There you go. So that's the V, which is S over T, or you can think of that as R times theta over T. So our radius was 4800 pi. And what does this come out to be?
19,200.
Alrighty, very good.
Wait, it's.
And this will be in.
It's not that. Sorry, I did multiply by. So it's actually 60,318.5.
Oh, I did the same thing, didn't I? I just did 4 times 4800 and left the pi out. Okay, so this answer actually is 4 times 4800 pi. It's coming out to be 60,318.57. So approximately 60,319. Now, what do you think your unit of measurement for this guy is going to be? Inches per minute. Yeah, very good. That's a lot of linear speed if you think about it, because again, we're talking about a saw blade, which is going to be a pretty small I guess length or whatever you want to think about it. So that's of course giving you quite a bit of a linear speed here, 60,319 inches per minute.
Okay.
Sure.
How do you find
The
central angle for angular speed?
oh, angular
At the
speed.
top,
This one, right?
yeah, the numerator.
Okay, so basically, again, they're telling us your blade is making 2,400 revolutions per minute, right? So when we're talking about a revolution, we're basically saying it's completing 2,400 circles in 1 minute. Now we know each circle is going to be having a total of 360 degrees, but we do our calculations in radians, so the 360 is the same thing as 2 pi, right? So if one circle is 2 pi, then 2,400 of those will be well, technically 2 pi times 2,400, but we're not just doing a pi calculation here. We're just multiplying the numbers, leaving the pi as it is. But this guy actually will come out to be, if you do 4,800 pi, I mean, you're talking about 15,079 or almost 15,080 degrees is what it's covering in that 1 minute, right? So what's happening here is then you take your angle, which is this degree measurement for the total of those 2,400 revolutions, 4,800 pi, and then let's go back here. Your angular speed is basically taking that angle, theta, which we're now calculating it to be 4,800 pi, and dividing it by t. Now your time, because this revolution, all of this is only happening in 1 minute, right? So your time stays at that 1 minute. So that's literally why these two answers come out to be the same, because we're not dividing it by like 60 seconds or anything like that. We're dividing it just by 1 minute because we're keeping our time in a minute.
Okay.
If we had changed our time to seconds, then you would actually be dividing by 60 seconds instead of 1 minute. So that's why your angular speed and your theta are going to be the same number in this case. And of course, they're both also measured as radians. Actually, this guy should only be radians. It's only radians per minute for the angular speed. Okay, so does that make sense how we came up with the 4800 pi? Yeah.
That's essentially just a full revolution.
And then multiply with how many times the rotation happens. And then your linear speed, you're again taking that same value of 4800 pi, but this time you're multiplying it with the radius of your saw blade. And our time still stays at 1 minute because again, all of this is happening in just 1 minute. So you're literally just multiplying the numbers on the numerator. 4 times 4800 pi. And for this guy, we're rounding it to a whole number instead of 2 decimal places.
All right, I got it now.
Yeah, all right, wonderful. Did anybody else have a question about this example? Okay. All right, so that was using the idea of an arc length and building up on that arc length with our angular speed and linear speed. Now we're actually getting into the area of a sector, or basically think about a slice of a pizza pie, right? A little wedge. Basically, that's what we're trying to think about. So as you can see, for the area of a sector, we need the radius, we need the angle to do this calculation. So obviously, when we're talking about a sector, think about it. We are going to have it bounded by 2 of our radius or radii calculations, and then of course the well, technically we don't really need the arc length in there, but that's definitely going to play a part of it. So we're talking about the area of a sector as being 1/2 radius squared multiplied by theta. Again, guys, keep in mind that theta is still in radians. We haven't switched from radians. So this one actually, I like this example. It's talking about a sprinkler on a golf course. So basically, we know it does that same shape where it's actually creating a sector when it's, watering your little area that it has. So in this case, we are saying the spray of the water goes to a distance of 70 feet and it rotates to an angle of 120 degrees. So we have our radius, which will be 70 feet. We have our angle, but again, your angle is given to you as degrees and not radians. So that's going to be our first step, is converting our degree into radians. And once we do that little conversion, then we're ready to put it into our area of the sector formula. 1/2 radius squared multiplied by theta. So that's our 70 degrees for the radius, 2 pi over 3 from our theta value. Multiply that together. And again, we're rounding it just to a whole number. So using that same example, let's look at number, what is this, 8? Okay, so they're telling us for number 8, the sprinkler sprays water over a distance of 40 feet. So that's going to be our radius. And the angle it rotates through is 80 degrees. So the first thing, of course, you're converting that into radians. Since we're converting it to radians, pi goes on the top. 180 degrees will go on the bottom. And you're just reducing that fraction down. So 80 divided by 180, what does that come out to?
1/9.
Yeah. This is basically 8 over 18 if you get rid of the 0. So just reduce that, and that will be pi and radians, right? 4 times pi over radians. Okay, so now we're ready for the area of the sector. So that was 1/2 radius squared theta. 40 feet to the second power, and then our theta is 4 over 9 pi. I would probably just plug everything in the calculator, so just be careful. You do have 1/2. If you want, you can type that in obviously as 0.5. So that would be 0.5 multiplied by 40 squared, because that is radius squared, multiplied by 4 over 9 pi. I think that should be it. So what did you guys come up with?
1117.010721.
Right,
How
okay,
many
so
places for decimals?
I think the example went to a whole number, so we'll do a whole number as well. So 1117.01, that's basically 1117, and what's your unit of measurement here? Yeah, because it's area, remember, and since you are doing r square, so that's your distance, the sprinkler sprays, so that's going to be square feet, or however you want to write it. Okay. So this is not letting me do. So some of these are going to be just the basic questions here. So yeah, so this is what I wanted you to show. You do have this one example in here, which is asking you to use the information given to you in degrees, minutes, and seconds. I want you to try this. If you have trouble with that, let me know, but I definitely like you to try that. This one here, again, kind of like our example that we did with the rotation of a saw blade. You should have this example here for your linear and angular speed, and then something like our sprinkler example. This one is talking about the windshield wiper. So I'd like you to try those word problems, see how you feel about them, and if you have any questions, let me know. And I'm actually going to go ahead and give you your handouts for the next